to give demo on post layout simulation of inverter, and the library here is 90 nanometer. So initially this is a circuit of inverter, but when we go for post layout simulation, we should make a symbol of the schematic. So for that we need to remove the sources, voltage sources. So let's remove the sources. This is input source, and this is supply source, and this is ground. So we have removed the sources here, and now again we have to give the pins to the input so that in layout it becomes easy. So here V in I'm giving, that is the gate of the inverter, V in here, and then we need to give VDD and ground. So now we are done with the schematic. You can check and save the design, so we don't have any warning and error. Now you can go for creating symbol. To create symbol, click on tab create and then cell view. From cell view, it means that we are creating symbol over the schematic that is available in cell view, and make sure that library name, cell name and those things are correct, and the view, from view, that is from schematic view, we're going to convert that into symbol. Click OK, and here you need to assign the pins in the symbol. Which are the pins that you need to come at the left, right, top and bottom? Mostly inputs we will have at left hand side, so we will take out ground and VDD. Right hand side we will have Vout, output pin. At the top we will have only VDD, and at the bottom we will take ground. So this is a pin configuration over the symbol. Now click OK. So here a dummy symbol has came with a square shape. Now you can change this shape according to the schematic which we have used. Here we have used inverter, so we need a triangle and a circle. So I am removing the guidelines here. Make sure that you only, that is, delete the square box. Do not delete the pins here, because those are the input output pins, and let the port name be. So here we will rename the port name, press escape, and then, so this is inverter design, so let it be INV. And now I'm going to create the symbol. These are the shapes available. Now since I'm going for triangle, I'm taking a line and just triangle I'm drawing. Yeah, so a triangle is done, and I need a circle shape here, so take the circle symbol. Okay, and now you shift the pins, that is the input pins, accordingly, so that it completes the symbol. VDD as at the top, ground at the bottom, and V on at the right. And then you can shift this, you can shift the symbol name so that it becomes easy for viewing. Now save the symbol, check and save. So now there is no error between symbol and schematic, so it has saved. So now that we have created symbol and the schematic, now let's test the symbol which we have just created. So now again I'm going to create a new file. Here John library is my 90 nanometer technology library name, which is custom to my design, and cell view I'm giving it to be INV_test. Yeah, so here I'm going to instantiate the symbol which I have just created, the inverter symbol that is available in browse. You browse the instantiate, that is available in my JR, that is JR library. Here John inverter is the file name. We have not created symbol for the other circuits, so we are not getting any view here. We have created symbol only for inverter, that's why we are getting view symbol. So you can select the symbol and instantiate that in your design, that's in your cell view window. So here inverter is we have got, and we need a source to the input, that is pulse input. We need a VDD supply, ground, and then output pin. So now we are taking pulse input that is available in analog library. Here V pulse, yeah, it is here, symbol, The pulse value is, that is lower saving is 0 and upper saving is 1 volt, and the period I am giving is 10 nano. So the pulse will be 4 nano, and raise and delay times are the 5% of the period, that is 500 pico and 500 pico. So this will be my input. Okay, now I need a VDD, this supply voltage, so VDC, VDC I have got. So that voltage level is 1 volt. Okay, I'm placing it here. So now I'm connecting input to the pulse and input is connected. Similarly, this is output pin, and this needs to be grounded. So I will take the ground symbol now, which is again available in analog lib. Okay, so 1, 2, 3 grounds I'm placing, and I need to connect the source and the VDD here. So I'm using a label, VDD label. So now I'm virtually connecting the source and symbol here. So this label is this label tells us that these two nodes are connected together. So now press escape. I'm saving the design. Two warnings are there, that means the output pin is floating, so it is showing warning. So we need to put a label here. So we will put a label output. This is our V out. Let's put label to input also, so that we can visualize the waveforms clearly. So now that the symbol is done, so let's go for the transient analysis and check whether the symbol is working. For that, go to launch, ADE, analog design environment, L. So here the analysis type I am choosing transient analysis. My pulse width is 10, so I'm going for 20 here, so that I will get a 2 cycle of input, 20 nano, and I have to plot input and output. So output to be plotted on the schematic, output and the input. Come to the AD window. So these two ports are selected. Now I can run the simulation. Yeah, this tells you that our symbol is working correct. So you can put input at the top. So when it is rising, output is at the bottom level. When input is on low level, output is at high level. So symbol is working good. Now close the waveform and close the ADE. We don't want to save the state here. Now after checking symbol, you again come to the schematic window. Yeah, now from schematic we need to go for layout. So in order to start the layout window, go to launch, layout Excel. So here I'm going to create a new layout, and configuration, the layout configuration will be taken automatically. Okay, again you make sure that library, cell name, those are correct, and here cell view is layout. Previously we had a schematic. Now since we are moving to layout, so the cell type has become layout. Okay, this is my layout window. So you could see here John inverter layout. So we are going to make layout of the schematic whose name is John inverter. In the layout you could see that we can generate. Here there are in the schematic there are 2 MOSes and 4 pins. So those MOSes we can generate directly, which the cadence will generate directly. Those are already optimized, these MOSes, so no need to design the MOSes again. We can just instantiate the MOSes. That we can do through click on the tab connectivity, generate all from the source. This shows that we are generating all the MOSes and pins that is available in the source. So let this default setting be as it is. Click OK. So here we have got the 4 pins and the MOSes alone. Now the work left is we have to connect MOSes and the pin together. If you press Shift F, you need to press Shift F so that you can see the internal view of the MOS. But here you could see that when we go for a schematic, in schematic we have source, body, drain and gate, but we have only 3 terminal here, that is drain, gate and source. Here source and body are tied together, but we need it to be detached. So what you do is you can go to schematic. In the schematic, select the MOS, go to its property. Here you could see that there will be a property name called body tie type. Defaultly it will be none. You need to choose detached there. Do that for both the MOSes. I did for NMOS, PMOS. Now I am going for NMOS. Again in NMOS, yeah, body type, it is detached. So I have detached body type. Body tie has been detached for both the MOSes. Now again save the design here. Come back to layout window. Again you can go to connectivity, generate all from source, the previous step which we did. It says that the previous layout which is there in the window will delete. Okay, so let this default setting be same. I have to click it. Okay, see, now we can see that source and body are detached here. Similarly here source and body are detached. Now our work is to make the connections. First let's connect this body and the source of both the MOSes. We could see here body and source are made of metal 1 layer. You can see the layers here. What are the layers available? Blue color defines that it is metal 1 layer. You can come and see here. You could see here blue is metal 1, crossed red is metal 2 layer, and yellow crossed is metal 3 layer. But here we need metal 2 layer in order to connect this body with the source. So what I'm doing is I'm choosing the move icon. I'm just moving this pin ahead. We need the pin to be at the corner of the active design area. This is the active design area. Even if you go for DRC or LVS, check will be performed only within the active area. So whatever the design is there, we should bring the design within the active area. So now I need to connect these two, that is these 2 ports of NMOS pins. So I'm choosing metal 1 here. Yeah, you can go to create, shape, rectangle. There are 2 ways we can connect the path. One is by using rectangle, another by using path. The difference is if you take rectangle and if you start drawing it, actually it will not be it will be of irregular shape. Again we have to come back and then resize the width of the wires so that the DRC rule matches. Instead of that, I'm undoing that. Instead of going for rectangle, you can go to shape and choose path here. So the difference is if you choose path, if you're starting with a metal, it will automatically size its width according to DRC rule. So no need to come and change the width according to DRC rule. It will automatically take care. The difference here is one thing you need to know. while starting at the point, you can just click a mouse click. If you have a mouse click, then it will start laying the metal one. If you want to stop at a point, then press enter, so that will stop at a point. If suppose you are starting from a point, and if you want to turn right or left, at that time left click the mouse, and then you can move either in the left or right direction. But if you want to stop at that place, then you have to press enter. These are the two ways of laying the metal layer. So now I'm going to connect these 2 points. So I need to start at the midpoint of the metal layer. Okay, so I have extended this. I'm pressing enter here to end this. You could see that edges have not matched here, edges of the metal. So I need to move this so that edges are matching. So now we are going to connect drain and the source and the body here. So I'm pressing P, that is P in the sense create. Instead of going to create symbol and path, the shortcut is we can press P in the keyboard. So in order to zoom, you can scroll the mouse button. So I'm starting from here. So yeah, so I have extended the body. Now I'm extending the source. Make sure that the edges are matching. If the edges are not matching, you have to move the metal so that edges are matching properly, else you will face DRC violation errors. And now I have to connect these two. So P, I have connected drain and body and source here. Similarly, now I'm connecting for nmos. You can see that body and the source is connected to both the MOSes. Since this is a small circuit where we have only 4 pins, the pin placement will not matter. So I am just placing the pin wherever it is. But when you go for a bigger circuit, you should plan the pin placement accordingly. So this, to see which pin it is, you can click on the pin and go to its check its property. Yeah, here in the property, go for connectivity. You will see that this is pin VDD. So we know that VDD should be connected to source and body of the terminal of PMOS. So I'm just placing that on the metal. So this means that since all are metal one, so VDD, body and source is connected. Either you can shift the pin to the metal, or you can drag metal, you can lay a metal between pin and the terminal. So I'm again checking the property of this node. So this pin is ground, that is to be connected with the NMOS. So I have shifted it at the top. So these two are done. Now the pending connect, yeah, our inverter circuit. So we have did connection of this part and this part, that is drain and body part. Now we have to connect both the drains to the output terminal. You could see that in the layout, these are the drains and this will be your output, that is V out. So I need to connect these 3 points. Again I am laying the path, metal path, starting from here. Edges are matching. So I am stopping at the middle. Again from here I am laying. Both are connected. Now I can start a pin from here. So now I'm going to move the V out pin. Okay, we have connected both the drains to the output. Now the input is pending, so we need to connect to the gate of both the MOSFETs. So we can just first extend the poly layer. So select poly here. I'm pressing on P, so it will adjust the width accordingly, poly width, which is according to DRC rule. So I'm starting from here, pressing enter, but you could see that there is a mismatch in the edges, so I need to move the poly to the right side. Yeah, so now the gate is matching. So now I need to connect this to metal one, but you could see that this is poly and this is metal one. So when we connect our two different layers, we need to have a via between them. So first let's start a metal layer from the input pin. I need to press P. I'm starting from here. I'm extending it till the poly, and I need to connect poly and metal one here. So I need a via. Via is available in tab create via. You can take from here. You could see that via definitions, metal 1 to poly via is there, metal 2 to poly, metal 1 to metal 2 to 3. So what are the vias are needed, you can take from here. For us, metal 1 to poly is needed, so I have chosen that. I am rotating it so that it can match the axis. Hide it. So I am placing it over metal and poly. So this ensures that both the pins are connected together. For now, we have connected all the MOSFETs and pins together. So now you can save the design.